Welcome to Networks Professionals.
Hey everyone, welcome. If you really want to get past all the hype and finally understand the actual nuts and bolts of how artificial intelligence works under the hood, well, you are in exactly the right place. Today, we are absolutely demystifying the core mathematical machinery of AI. It's a concept called gradient descent. Let's get right into it. So here is the big question. How does an AI actually learn from its mistakes? I mean, really, when a neural network completely misidentifies an image or, spits out a really clunky sentence, how does it know to do better the next time? It isn't magic, right? It doesn't just sit there and think harder. Actually, there's a highly specific, beautifully elegant process at play that actively corrects its predictions. Let's look at exactly what that is.
And the answer to that is gradient descent. This is the fundamental math that corrects AI predictions. Basically, it's the primary optimization algorithm used to train these models, and its entire purpose in life, its one job, is to minimize the error between what the AI predicts is going to happen and the actual real-world results. Now, to truly appreciate the sheer scale of what this math accomplishes, we need to look at its role in the broader landscape of deep learning.
Section 1. The engine of AI, powering deep learning.
The engine that enables neural networks to learn. Man, this quote just perfectly captures the gravity of what gradient descent actually is. Think about it. A neural network is made up of countless internal parameters, specifically things called weights and biases. You can kind of think of them like millions of tiny interconnected dials. Gradient descent is the engine that iteratively adjusts every single one of those dials, just turning them slightly this way, maybe a little bit that way, over and over, until the absolute smallest possible error is achieved. When you hear about a modern AI having billions of parameters, yeah, those are the exact dials being turned. But how does it actually know which way to turn them? Well, to grasp this abstract math, we're going to use a physical metaphor.
Section 2. Navigating the lost landscape, the metaphorical journey.
Welcome to the lost landscape. Okay, I want you to picture the AI as a hiker who's been just suddenly dropped into a massive, foggy, rolling mountain range. Our hiker can't see the entire map, but they have one very specific, absolutely critical task. They must find the absolute lowest point in the entire valley. Now, in this landscape, altitude literally represents error. So finding the absolute lowest possible point, that means the errors are minimized.
Now, what's really interesting here is how the cost function acts as our altitude meter on this hike. It acts as a barometer for accuracy. The AI is constantly checking this cost function, which measures exactly how far its current predictions are from the target data. So a lower value on that cost function means a lower altitude in our landscape, which ultimately means a far better, far more accurate model. Okay, so we've got our hiker, and we have our altitude meter. But how do they actually walk down the mountain?
Section 3. The 5-step journey, reaching the lowest point.
Okay, let's dive into this specific challenge. Because if the landscape is foggy, how do we actually get to the bottom without just wandering aimlessly? Well, the algorithm relies on 5 highly specific procedural phases. Let's look at the exact phases it follows.
It all happens in 5 very logical steps. First up, initialization. The model starts with completely random parameter values. Basically, our hiker is dropped at a random spot on the mountain. Second is error calculation. We check our cost function to see exactly how far off our predictions are. Third is gradient computation. Now, using calculus, the algorithm determines the gradient, which is essentially the slope of the error curve right where the hiker is currently standing. Fourth, the parameter update. The model takes a small, calculated step downhill to reduce that error. And finally, step 5, iteration. We repeat the cycle over and over and over again.
And all of that repetition leads us right here, to convergence. Convergence is the ultimate finish line of our hike. It's the state we reach when that iteration cycle repeats so many times that the error just stops decreasing significantly. Our hiker has hit the valley floor. There are simply no more steps downward left to take.
So the crucial takeaway here is that the algorithm always uses the negative gradient to guarantee it's moving downhill. See, the mathematical gradient actually points up, toward the steepest ascent. But since our goal is to minimize error, we move in the exact opposite direction, the negative gradient, to confidently step down toward that local or global minimum. But wait, there is a physical danger to our hike here. It isn't just about the direction we walk, it's also about how we walk.
Section 4. Perfecting the step size, the learning rate.
Meet the learning rate. This is a hyperparameter, which basically means it's a setting configured outside the model itself, and it acts as the ultimate pacing control for our AI hiker.
It strictly controls the size of each step the model takes down that mountain. And this brilliantly illustrates the Goldilocks problem of machine learning. If your learning rate is too high, your hiker takes massive, erratic leaps, totally overshooting the minimum and bouncing wildly back and forth across the valley. But if your rate is too low, your hiker takes microscopic steps and the model training becomes painfully slow. So you see, it literally has to be calibrated perfectly.
Let's look at a perfectly isolated, simple cost function to really see how this builds. Imagine a perfectly smooth, U-shaped valley. We're going to represent it by the function f of x equals x squared. Gradient descent starts us at a completely random x somewhere on the steep sides of this U-shape. Our ultimate destination, the absolute minimum error, is dead center at the bottom, right where x equals 0.
So how does it step towards 0? Well, by calculating the slope at each step using the derivative, f prime of x equals 2x. Using calculus, we find the slope of the error curve at our current point, to literally point us down the hill. It calculates the exact slope of the error curve at our current position, ensuring every single step we take mathematically pushes us closer and closer to that perfect 0. This simple piece of calculus, this is the absolute secret to an AI learning.
So we've explored the loss landscape, we've taken the iterative steps downhill, and we've finally reached convergence. Gradient descent is the undisputed engine that enables neural networks to learn today. But, it leaves us with a really fascinating question to ponder. As models grow infinitely more complex, and these landscapes become so much harder to navigate, if gradient descent is the engine right now, what incredibly advanced mathematics will power the AI of tomorrow? Thank you so much for joining me for this explainer. Keep asking questions and keep learning.
Thanks for watching.